Hello, and welcome to this problem number 968 binary tree cameras. So, as you would have seen, I have actually changed in the camera setup a bit. Instead of the left side, my face you will see on the right side. That's simply because I realized that the way Leetcode IDE is set up, a lot of the space is actually taken up by this entire thing, and rather more focus should be on the coding window and less focus should be on the question window because once you have read the question, you don't need it as much. So this is gonna be the setup here. Of course, there is the run code and the submit code button which is hidden, but I could just say it and you would know, right? So let's get started. So this problem says that given a binary tree, very important. Given a binary tree, it's a binary tree. We install cameras on the nodes of the tree, right? Each camera at a node can monitor its parents, itself, and its immediate children. So three things: its parents, itself, and intermediate children. Calculate the minimum number of cameras needed to monitor all the nodes of the tree, right? So what you're supposed to do is you're supposed to put in cameras. You could put cameras on any node, and the cameras have this property that the camera, it can monitor the node which it's on. It's like intermediate children, like all the children, and it's right. This is what the camera can do. And you want to find out the minimum number of cameras you need to put in a given binary tree so that all the nodes are monitored, right? So actually a simple like actually relatively a simple question. So it's basically not a very complicated question. It's relatively a simple question, but this question is it actually gives you a detailed discussion of how you should think when you have problems like these, where including the children of the node, the parents of the nodes are all also involved. So this is one category of problem I wanted to cover. So let's look at this example quickly. Example one. Now here, as you see that if you so this is the binary tree. If you put camera here, this camera would wait a minute. This camera here would make sure that the its parents. So this is under view. This is also this is also something which is covered. So the camera covers this node itself, the upper nodes, the lower node, and also the so this entire tree is covered by just one camera, right? So you only need one camera for this tree. In the second example, you might actually need more than one camera. So let's look at that case. So in this tree, you could have put camera anywhere here, but look at this camera placement. If you put a camera here, what happens is that a camera placed here is covering this thing. It covers this, like its immediate child, its parent. A camera put here covers its immediate parent. It also covers this. Now this is actually covered two times, and we want to minimize such instances where it is covered two times. But it so happens that in this configuration, this is the best possible we can get. You cannot do anything with one camera, because if you put one camera even here, these two nodes would be left from being covered, right? So you need at least two cameras to do this. So the answer to this is two, right? So this is actually a very it's it has you have to have two very important observations to handle this problem. So this is the structure of the binary tree. There is a left, there is a right, and there is a value. You don't need to let's not remove this because I mean it's not needed. In some problems it's actually needed a lot, but you just need to know left, right, and so on. So like now see, in this problem what we need to realize is that a node can affect its children and its parents. This is a very important statement. In this problem, a node can affect its children and its parents. In a lot of the problems, a node can only affect its children, and it is very easy because for the tree, we have nodes which are pointing downwards. Like for every node, we have a left node and a right node, and so you could very easily access a left node and the right node. You could do it very easily. But if you want to, let's say, given a tree which has like those links, how do you access a parent of a node? So this actually makes the problem a little bit more challenging, and there are these classes of problems which actually need to dealing with parents of the trees. So there are many techniques of actually doing that. Actually storing, keeping things in stacks and storing that. But one good heuristic when you see such problems is to remember that the way you do it is the way you do whenever you have the you from the children you want to go to the parents. The best way to do it is do it via DFS, a depth first search. What does a DFS guarantee, right? So Now, what happens in a DFS? A DFS, what happens is you start with the root node, you go to the most bottom part of it, and then by recursively stack calling, you come back, you come back, you come back, right? So DFS is intuitively one way in which you could go down the tree, you could go down to the leaf nodes, and from the leaf nodes you can come back, right? So basically, if you don't want to use DFS, you could store the parents in some data structures, and there are many fancy algorithms and fancy ways of doing it. But I think the the structure remains the same. Even if you use a data structure, it's like DFS. When you do in DFS, it actually uses recursion to come back, and it the backend recursion actually uses stack, right, to handle this. So it's like we need some sort of a storage to actually go back. You need some sort of a storage when we have children affecting their parents, right, in a binary, right? So this problem actually is a very straightforward problem, because if you look at this problem, what you need to do is you just need to go down the tree. Excuse me. You just need to go down the tree, and you just need to see, okay, there are two properties a node can have. Like, what are the two properties a node can have? There are important two properties a node. Please don't mind the spelling, it might be wrong. I'm not an English nerd. So the two properties, the first property is that it has a camera, right? And the second property is that it is monitored, right? So the first property implies the second one. If the node itself has a camera, then it's monitored by itself. And the second thing is that if the node is monitored, then what we get is that we don't need to put a camera there, right? So you could, so the combination, if this is a, all of these are like bools, right? These are bools. This is a boolean variable, and this is a boolean variable, whether a node has a camera or it's monitored. So what we want to do is we want to make sure, we want to place the cameras in such a way that this second variable is monitored is true for all the the entire tree, right? And what we do is we actually do a depth first search, and when we do a depth first search, we need to we actually, for every node we have this property, it has a camera, and like it is monitored. And what we do is, if so you're coming from bottom up, so like, yeah, so the advantage of this is bottom up, right? You're filling the cameras bottom up, and if you're coming from bottom up, you realize that if you have a node, for a node, if it's if both of its children, if both of its children aren't monitored, then that is the only way you can monitor those children is by putting a camera on that node, on the node. So we are on the node. So the only way you could monitor, if both of its children are not monitored, then the only way you could put a camera is, basically by but the only way you can solve that is putting a camera. And since it's a binary tree, you cannot have like more than one parent and things like that. You just It's just one parent. The only way those two nodes are going to be monitored is by putting a camera on that node of the parent, right? The second characteristic is that, let's say, if the second characteristics is, yes. So if basically the as I was saying, the second property is that if one of the child actually has a camera, then you don't need to do anything. You just need, now that the node in question is monitored, right? So if one of the children have cameras, then you're pretty sure that this node is monitored. And when you put a camera, it directly implies that this node is monitored, right? Yes, monitored, right? So see, what did you do? If you are at a node, and if both of the children are not monitored, you have to compulsory put a camera there, because there is no option for the kids to get monitored. So but by doing that, you make the node being monitored, and you also put a camera on that node, right? And if one of the when you are coming to a tree, and when you have one node which has two kids, two children or one child, and one of them has camera, if one of them is actually monitored, then what you do is you put a camera there, right? Because you don't need to put a camera there, you just see that the node is monitored itself, right? Because if like yeah, if one of the children has monitored, then the node is monitored. So it's pretty straightforward. right here. So it's just going back again, you're doing a DFS, so you're coming from bottom to up. If you are at a particular node, you need to do this for all the nodes. So if you are a particular node, if both of its children are unmonitored, you need to put a camera there, and that's how the node and its kids become monitored. If one of the child has a camera, then you just know that this node is monitored. You don't need to do anything else, right? And then you do it recursively for all the node, so either of the condition will be true. So in both of the cases, all the nodes will be monitored, right? And in this greedy fashion, you will use the minimum number of camera, because you're going from bottom up. If you're going from top up, you need to check all the possibilities and things like that. But since you're going from bottom up, it's automatically greedy. It's automatically the fact that you're being optimal at putting cameras, right? So there are many ways of implementing this. So let's like a decent way of implementing it would be to have a global variable, let's say n camera. So in this scope, you say, first of all, you begin with saying that this is 0, the number of camera is 0, and you somehow have a function. Okay, so this is you one other consideration needs to be done. What about the leaf nodes, or what about the root node? So we'll actually come to that, right? So the number of cameras. Now I'll have a variable. Let's call it the answer variable, or let's call this s a variable, to like a temp variable. So this temp variable is auto temp. It gets in this function cnt cameras, and this function takes in root. So it takes in this what it does, it takes in this function, and it does something. Let's basically talk about implementing this function and seeing what's the most efficient way of doing it. So okay, so let's have, so we need these two, so we need it to return two variables. So auto, let's not have auto, let's have a pair of bool, right? So you have this pair of bool a temp. The first one says whether the bool, like pair dot first is like whether the camera, it has camera, and two is like whether it is monitored or not, right? So this is basically the situation of the root node, whether the root node is monitored or not. So what this will do is it will actually do the DFS from the root. There is this external variable called camera. It will increase the number of camera, like the n camera, as and when it finds worth increasing, and then finally it will tell us about the root node. Right now, root node needs to be specially cared about, because root node doesn't have a parent, right? So if root node does not, so if basically if the root node is not being monitored by something which is below it, the only possibility you have is to put a camera at the root node, right? So this is just that special case of looking at the root node. So if you see that, if it's if this temp is like the condition of the root node, if the second value of it, so it's not monitored. So if the temp dot second is false, right? So it's like it's not being monitored. If the root is not being monitored, the only option we have is that we put a camera on the root. So we increase the number of camera. We have to increase the number of camera. We put the camera on the root. That's the only consideration you have, and then you return the n camera variable. It will be much more clear when I actually write the proper function to this, right? So let's do that as well. So we have this. We'll have we'll have some space for some real estate. Okay, yeah. So we're writing this function. This function returns a pair of bool pair of booleans. What is this function? The function is called a cnt camera, right? Cnt camera. It takes in tree node, pointer to tree node of root, right? It takes in this. Now when it does take this thing in, yeah, this thing was not needed, because yeah, this is what can go down, right? So cnt camera, right? So first of all, you need to know what is with the root node. So if the root node is null, right, as generally all tree problems, what if the root node is null? If the root node is null, first of all, you don't have a tree. So in the base case, when the root node is null, you actually handling it with you just put a camera on that root node and then you're done. So that is handled by this. The only case when you need to take care of it, when root node is equal to null, is when you are actually at the leaf node and somebody is actually trying to check, or you're in one of those nodes which don't exist. If the node doesn't exist, then you just simply say that it's like there is no camera there, so there is no camera here, and it's already monitored, or you don't need to care about it. So this is like, is there, the first thing is like, the first value is this have a camera. Second is it monitored, right? The first bool is it have a camera and is it monitored. So you say the null value doesn't have a camera, and true, because it's actually, we just say it's monitored because you don't care about what is happening to this. So if the algorithm will totally ignore this if you are at the null position, even at the leaf nodes, or you are at the one of those side positions, right? So this is done. Now let's get into the more interesting cases. You are returned, since this is an explicit, the function has like pair bool bool returning, this will automatically be converted into a pair boolean boolean. If you want to explicitly do it, you could do explicit type conversion, but it's not necessary because the return type of the function is pair bool bool. Okay, so you have pair bool bool of left. So this is nothing but when you were doing this for the left part of the root node, right? You're doing this for the left part of the root node, and similarly you will have, just remember that the first value is, I'll put it here as well so that it's clear for anybody, that in this function the first thing, the function dot one, like, is it camera, and the second thing is that is it monitor, right? So left and right. So once you, so this is actually doing the post order traversal. So when you're doing a DFS, you could do it in three ways. You could do with, a pre-order, in order, or post order. This is actually a post order traversal because you first need to look at what left and right are, and you need to do it till the end of it, and then based on the left and the right values you can make a choice whether you want to put a camera or not, right? Because you need the values for both, whether there's a camera on the left and right, to make a decision of about the root node. So like about the node, the parent node. So this is actually a post order traversal, right? So now you say that if we just handle this case that uh, if both of the children are on monitor, you need to put the camera. If one of the children has cameras, not have camera, one of the children has camera, then the node is monitored. So if, let's check that. So if one of the kid has cameras, how do you see that? So this is the left child, so you just say if left dot first, so this has a camera, or right dot first is true, or both, whatever. Both will actually not be true, like in an optimal setup, but like if one of them is true, it might also be. So if one of them is true, what you do is you just say, okay, you'll have to initialize these two bools, bool hascam, right, which is false by default, and bool monitored is also false by default, right? So what you do is, you just, for like, if this is true, then you don't need to if this is true, then you don't need to have a cam, so this lets this remain false, but you now know that this is actually being monitored, right? That's cool. If there's this other case in which like if l dot second, so basically both of them are not there. So if both of his children aren't monitored, so if you want to see both the children aren't monitored, so there where you have the second boolean variable, so like l dot second is false, and L dot, like R dot second. So both of the variables are not monitored. Then you need to make sure that the hash cam becomes true. So this node should have a camera. Number of camera is monitored also becomes true, because it has a camera, it automatically becomes monitored, and the number of camera has to also n camera increase, right? So that's how why we have a global variable called n camera. This has to increase. This is all handled. This is all the case. That's pretty much it. For the left, for the right, and so on. And finally, you will need to return we just say we return hash cam and monitored, right? So for whatever the case may be, this whether this is true, whether this is true, this will be returned hash cam monitored of the values. And if nothing is true, then both of them will be false. It will never happen. So let's pretty much submit this solution. There is a silly mistake. We'll debug it. Run this solution first. Okay, so there is a silly mistake. Let's see what that silly mistake is. So actually the silly mistake was rather aberrant. It's actually right here. So I just like R was being left. So let's try to do this now. Let's try to run this now. Accepted. Let's try to submit it and accepted. Right, it's better than 73%. Memory use is 56%. So a decent, simple solution to the to this question, which was just uh, breadth for like a depth first search followed by like the post order traversal followed by a greedy approach of assigning cameras. So it's actually a straightforward question, but just this intuition that when you need to have children that can affect its parents, you need depth first search, and the fact that you needed post order traversal was a little bit tricky, but overall it's a simple question. You could easily have solved this in, let's say, a half an hour time, right? And this is a pretty optimal solution. So it is interesting actually to see for cases in which you have an n array tree and you have like more nodes. How does this generalize? Because if you have an n array tree, you still need these binary variables, but you need to do this for like for all the nodes and all the trees. So this question can be asked in many variants, where you could have like more than one types of cameras. Each of them have different properties. So then the binary 1 and 0, like just being having a camera and having monitors is not enough. You'll have to make sure that there can be more cameras and more monitoring. So let's say we have to put two cameras. So like there can be many variants to this problem. But at the core fundamentals of this problem is about post order traversal and this greedy approach. So hope you enjoyed this video. And I really want to say that if you're watching until this end, please, if you have any suggestions for the videos, please put them in the comment section, that some new videos on this topic or these questions need to be made, and I'd surely try my best to make them. Right. Thank you.